What you're looking at here is almost certainly the most technologically advanced Chevy Stovebolt straight six ever built. Automotive specialists put this together, and we're going to show you how they managed to get 2 turbos and 6 individual throttle bodies all working on 50s era technology like a dream. Okay, so technically our engine isn't a Stovebolt. Stovebolts refer to the first generation of the Chevy straight six that ran from 1929 until 1936. And the way I understand the story is they were called Stovebolts because the bolts on the valve covers are slotted and resemble the same bolts used in wood stoves. But our engine came from a 1958 Chevrolet truck or heavy-duty vehicle of some sort. So that makes it a second generation engine. Still, this is an ancient piece of iron, and we are taking it places that it was never intended to go. So that is pretty cool. So our straight six is going into a 50s era Chevy Suburban that's going to be a hot rod build being done at Johnson's Hot Rod Shop in Gadsden, Alabama. Now, the Suburban will start looking something like this, even though this isn't the specific truck. But I'm told it's going to be a showstopper when they're done. Now, I can't show any pictures of it because Johnson's doesn't want anything to get out before they debut the truck at a big hot rod show coming up, which I understand. But they have given us permission to cover the engine build, which at the Horsepower Monster, that's what we're all about anyway. So Johnson's and their friends at Automotive Specialists often team up for these engine builds that go in these cars that are serious award winners. And they've done Y blocks and some really trick LSs and other stuff. But this straight six may be their greatest achievement yet, if you ask me. It is going to take everything Keith has in his bag of tricks to make a performance engine out of what has always been known as Chevrolet's boring base motor. And I think it's absolutely going to be interesting to a horsepower crazy crowd like you. But first, let me remind you one more time, if you have any interest, check out our new shirts. We've got some cool Horsepower Monster shirts. Little guy's name is Elvis, by the way. And if you're interested, you can get one cheap at the link below. Anyhow, that's enough sales stuff. Let's get back to it. Even though we'll be practically changing everything else, the foundation for this build is still a stock 261 straight six casting from 1958. Keith said he was able to open up the cylinders 30 thousandths over from the stock 3.75 inches to 3 inches 780 thousandths, but the cylinder wall thickness was still in the safe range at a minimum of 153 thousandths. A common theme you're going to hear throughout this video is the lack of good aftermarket performance parts available for the straight six. Now, Chevrolet never treated the straight six as any kind of a performance engine, and the aftermarket never put much effort into building parts for it. So there's just a lack of good stuff out there. For example, Dorton couldn't find quality bearings that met his requirements, so he used an old stock car racing trick. He installed a set of standard straight six bearings, then lined home the block with the bearings in place to open up the ID of those bearings to match the outside diameter of a modern LS bearing. Now the original main bearings serve only as a spacer to hold the modern coated LS bearings. In the old days, race engine builders did this to reduce the main journal size and cut down on rotating friction. But for this application, the work was done just to be able to use better bearing technology. The crankshaft thrust is still controlled by the original stock thrust bearing. Along with the block, we're also using a stock original crankshaft. Keith felt it had plenty of beef to hold up to the power levels we expect, so he had a company called Shaft Tech turn the crank to his specs. As you can probably guess, the main journals have been turned down to LS size 2 inches 559 thousandths to fit the new main bearings. The rod journals have been turned to 2 inches 200 thousandths, which, if you know your big blocks, is going to be a pretty familiar number. Even though the rod journals have been ground down, Keith didn't want to add any stroke, so they've been ground on center and not offset. While Shaft Tech had the crank for turning, they also nitrided it to harden the journals and make them more resistant against wear. And by the way, check out that big old chunk of iron for the center counterbalance. Thankfully, that's something you don't see in modern engines anymore. Another significant upgrade Keith made to the engine is the rear main seal. The straight six originally came with a rope seal, but that simply isn't good enough for this build. So Keith found a quality one-piece rear main seal that was at least close to the correct size. It turns out to be for a diesel Ford, by the way. and then machined the crank flange, the block, and the rear main cap to make it all fit. Anyhow, now that the crank is in place, you can see how the mains sit in the LS bearings, which are in turn supported by the original bearings. As long as you have the right amount of crush, there should be no worries about spinning a bearing. With this shot, you can see one of the weaknesses of this engine. There are only 4 main journals supporting the rotating assembly. Now this was fixed in the 3rd generation of this engine, which appeared in 1962 and had 7 journals. Personally, I don't know how much horsepower this crank can handle with only 4 points of support, but it's definitely something to keep in mind. To help add a little bit of strength, Keith replaced the center 2 main caps with billet steel units. He also had dowel pins added and machined the block to accept the pins to eliminate any chance of cap walk. The outer 2 main caps he left as the stock castings, explaining simply that they are huge and going with billet steel units likely wouldn't help any. The original mains used new 1/2-inch bolts and are torqued to 100 foot-pounds. The fasteners for the new billet caps, meanwhile, are a bit larger at 9/16 and torqued to 120 pounds. And with the crankshaft secured to the block, we are ready to move on to the rest of the rotating assembly. Keith had Diamond make these custom piston forgings for the build. They are sized at 3 inches 780 thousandths, which is 30 thousandths over stock. The pin bores are 990 thousandths, which of course is a big block size. That's because the connecting rods are big block forgings from Monar Technologies. They measure out at 7 inches 100 thousandths long. The one main difference between the modern H-beam big block rods and the original units that came out of the straight 6 is the new rods are much narrower. Normally, the connecting rod's lateral position is controlled by the cheeks on either side of the crankshaft's rod journals. This keeps the rod centered on the wrist pin, which is important because if the connecting rod is off-center on the pin, it can cause piston wear problems. That's not possible here because the journals are so wide. But Keith went with a stock car racing trick by having the pin bores brought inward to guide the rod's location. Few engines are actually piston guided because it can be tricky to get right. Can't be too tight or else you'll have problems, and too loose isn't much better. Here you can see the shim on the left-hand side of the connecting rod that Keith uses to dial in the correct end play and location. Anyhow, with the pistons 30 thousandths over and the stock stroke, that raises the displacement of the engine up from the stock 261 cubic inches to 265, so not much more. The Monar rods utilize 7/16 ARP rod bolts, and they're torqued to 80 foot-pounds to achieve the required 5.5 thousandths of an inch of stretch. Here you can see just how much rod side clearance we have with the narrower big block rods. A lot of people will worry about oil control, and we will lose oil out of the big end of the rods, but Keith says as long as you have a good high flow oil pump, it won't be a problem. Let's move on to the camshaft, which is also really cool. Like with the bearings, there were no aftermarket performance cams available to meet Keith's requirements. After all, the original 261 never came with roller lifters, so he had his own large diameter cam cut to his exacting specs from billet tool steel, and it is a beaut. The block's cam bore has been honed oversized to accept a 50mm cam and given high quality roller bearings. This is a solid roller cam with 250 degrees of duration at 50 thousandths tappet lift for both the intakes and the exhausts. It's also equal lift for both the intakes and exhausts with 374 thousandths at the lobes. So with a 1.74 ratio rocker arm, that'll come out to 550 thousandths of an inch of gross valve lift. Notice the collar clamped onto the shaft of the cam just behind the second lobe. It's a custom touch that's cool as glacier ice, but we'll have to get back to that in just a minute. Instead of a timing chain, the straight 6 uses a gear set like you see here. We're keeping that for this build. But for extra durability, Keith did fabricate this oil squirter that taps into one of the oil galleries and provides a small but steady stream of oil right between the gears where it's needed. Mating to the camshaft will be a set of tie bar roller lifters. That's a pair of them on the right. For comparison, we've got one of the original solid flat tappets on the left. Boy, have we come a long way or what? As Keith checks the cam timing, you can see one set of the lifters in their bores. The tie bars just barely clear the block, but just barely is good enough in this case. So we're good to go. Now let's get back to that collar on the camshaft I teased you about earlier. Keith plans to run port fuel injection on the straight six, controlled by a Holley Terminator X-Max ECU. But that system requires both a cam and crank position sensor, neither of which this engine has any provisions for. Heck, that stuff wasn't even close to existing when this engine was designed. That cam collar is an ingenious workaround. It's custom machined with a magnet in one side. After degreeing in the cam, Keith is able to adjust the position of the collar exactly where it needs to be and then locks it down tight. For the pickup, he machined a plate that bolts over the fuel pump boss and has a threaded hole for the pickup. Once the pickup is set, so there is somewhere between 60 to 80 thousandths of an inch between the pickup and the magnet, it should be good to go. Now, when the number one piston approaches top dead center, the ECU knows the camshaft position and can tell if it's a compression or an exhaust stroke. Pretty trick, and in my mind, this is the kind of craftsmanship that separates true engine builders from assemblers. Keith also fabbed up a new pickup for the stock oil pan. Remember, this engine will use port fuel injection and digital ignition controls. Since there will be no distributor, there's no need to put a distributor gear on the custom camshaft. But that also leaves no way to spin the oil pump. So we'll be using an external oil pump that's driven by a belt off the crank pulley. That's what the new pickup and plumbing to the side of the pan is for. The Terminator X-Max ECU also requires a crank position sensor. To make that work, Keith will be measuring off the flywheel from spec clutch. What you see here is an adapter plate that allows the straight six to mount up to a conventional Chevy small block bell housing to provide more transmission options. But you can also see where a hole has been drilled and tapped into the adapter plate to install a crank position sensor. It'll read off of one of 3 magnets installed into the flywheel every 120 degrees along the perimeter. The sensor can sense the magnets as they spin past because the flywheel itself is non-ferrous aluminum. Now the Terminator X-Max can read both the crank and the camshaft positions independently and accurately. Pretty cool how you can do this on an engine that was designed nearly 100 years ago. Another huge upgrade for this straight six is a cylinder head casting that's a reproduction of the famous old Wayne cylinder head. Back in the day, the Wayne cylinder head for the six was a game changer. We're talking about a design that's radically different from the stock version. For reference, here's an original Chevy straight six cylinder head. Now it's a bit crusty, but at least you can see what's going on. The original design had an absolutely whack combustion chamber with the intake and exhaust valves on 2 different levels. The head also has the intake and exhaust ports on the same side, which was common for that era. But the ports themselves are absolutely horrible. The intake ports feed 2 valves each. And here's a look inside the center intake. And yes, that's a wall the incoming air and fuel crashes right into before having to drop down on either side. The exhausts are just as bad. The Wayne head, meanwhile, is much more advanced. If you look at it with no frame of reference, it's not that big of a deal by modern standards. For example, the combustion chamber shrouds the outside of the valves pretty badly. But when you realize you shouldn't compare it to a modern LS head, but against the ancient head it was meant to replace decades ago, you can see what a big improvement it really is. Besides the much improved combustion chamber, the Wayne head is also a crossflow design with the exhaust ports on the opposite side of the head from the intakes. The intake valves are sized at 1 inch 940 thousandths in diameter, while the exhausts are 1 inch 550 thousandths. The chambers are sized at 72 cc's, which is pretty large for this displacement, but we'll take care of that with a little turbo boost. Another improvement with the Wayne head is the raised intake ports, which helps get air into the combustion chambers efficiently. The stock intakes are low and 90 degrees to the valve, which definitely hurts flow. Up top, the valve train is completed with a set of aluminum roller rockers on a shaft mount system. Like I mentioned before, the rockers are a 1.47 to 1 ratio, and gross valve lift will be 550 thousandths of an inch. They'll be activating a set of beehive valve springs with an installed height of 1 inch 760 thousandths. On the seat, those springs will have 200 pounds of pressure, and at full lift, that ramps up to 430 pounds. Notice that there is no lip around the top of the cylinder head to hold in oil when you pull the valve cover. I think that there's a bolt-on spacer for this head that serves that purpose, but with all the changes we've made, it won't work here. We'll just have to be careful to keep oil from getting all over the place whenever we have to pull the valve cover to check lash and other things like that. So far in this build, we've already seen a lot of cool touches, but it only gets better from here. Johnson's, an automotive specialist, wanted to design an individual throttle body intake for this engine, and it took a lot of custom work to make it all come together. It all starts with this CNC machined aluminum plate that blends the round throat of the throttle bodies into the oval intake ports. Also notice the openings both above and below the port. These are balanced ports or runners that connect all 6 intake ports. These create a common plenum between all the runners so that each throttle body sees the intake pulses from all the cylinders and also provides a place to connect a map sensor. The end result is an engine that's easier to tune and runs much more smoothly. Mounted to the balance port plate are these 3 adapters cast specifically for this engine. The Borla throttle bodies we'll be using are paired up and a bit wider than the pairs of intake ports, so the spacers artfully blend the airflow down and into the ports. And finally, the 3 Borla throttle bodies are bolted up. Each contains 2 individual runners. The Borla system is CNC machined from aluminum instead of cast like the old Webers they're meant to emulate. They are also fully modernized with fuel injectors where the float bowls and Weber carbs would be. Plus, they're also compatible with everything needed by modern ECUs. On the opposite side of the engine, these are the 2 stainless steel exhaust manifold castings that'll direct the hot exhaust gases into the 2 turbos. Like the intake pieces, the exhausts are one-of-a-kind castings specifically made for this build. Mounted to the exhaust castings are a pair of Garrett Gen 2 GTX turbos. Now, these aren't the biggest whirligigs ever made, but they are perfect for our engine. The Garrett GTXs are built with ceramic ball bearings and a super efficient compressor wheel to help make great boost in a small package. 2 of them might even be a bit of overkill when we only need to make 500 horsepower, but hey, show car. There's no denying that these just look awesome. Wastegates from TurboSmart clamp to the fittings just in front of the turbos. Now this may surprise you, but it turns out nobody makes an off-the-shelf kit for a Chevy Straight 6 to feed air from 2 turbos into 6 throttle bodies. And yeah, that was sarcasm. So, once again, a custom solution had to be made. This plate Keith is installing O-rings on is designed to mount across the tops of the throttle bodies and form a base for an intake manifold. As you can probably tell, it's CNC cut from a single piece of aluminum. It also forms a short intake horn to help guide air into the throttle body runners. On goes yet another O-ring into CNC cut grooves, and then Keith installs the gorgeous ribbed plenum top. So the plan is to run the boosted air through tubing to a pair of air-to-air intercoolers, and then from there into the intake manifold. Here's how Keith describes their thinking behind the setup of the unconventional intake and exhaust systems.
But we worked together with Johnson's Hot Rod Shop to develop the intake manifold, which and using the Borla EFI throttle bodies. And we knew we wanted a isolated runner look, but also we needed a balance chamber for the map sensor to work and for the idle and so forth, for it's got to be street driven. So we have a little small plenum that's sandwiched between the intake manifolds, which are cast, and the cylinder head, so we're getting our map for the boost reference and all off of that. And kind of the same thing on the exhaust. and Johnson's had the exhaust manifolds cast, which, as you can imagine, was very time consuming, took a lot of effort, a lot of time. But a couple of reasons for that. One with the heat of the turbo, and the other was mounting the turbos. They're so solid, with thick stainless steel flanges and all on them, that the turbos can mount on them and never have to worry about any flexing or leakage or anything like that. So it should be a very solid, durable, user-friendly piece.
Now, here's a look at the pretty complex front drive setup. Everything gets mounted up on the custom machined front plate. During development, Johnson's Hot Rod Shop actually sent over 3D printed mock-ups to automotive specialists so that Keith could test them out and suggest changes. The water pump may look a bit unusual. That's because it's actually off of a BMW, chosen for its small size. Also spinning on the main serpentine belt are a power steering pump on the driver's side and an alternator and AC compressor on the passenger side. The external oil pump mounted down low on the driver's side requires a cog belt, so it gets its own setup spun by the crankshaft. That's a lot of stuff to get mounted and make work when you're also trying to squeeze in turbo plumbing and intercoolers. Grandma called this squeezing 10 pounds of stuff into a 5-pound poke. And in case you aren't aware, poke is just Southern for bag. Anyhow, before we head to the dyno, I wanted to show you the ignition coil and oil filter mount setup. In this shot, the coil isn't squared up yet. The idea is that mounted here, the coils and all that unsightly wiring is away from the exhaust heat and also low and out of sight once the engine is mounted in the Suburban. Also notice the copper colored hardline running laterally just above the oil filter. This is plumbed into a pressure line coming out of the filter mount, wraps around the front of the engine to this distribution block, and feeds clean oil to the two turbos. Mounted to the front of that block is a TurboSmart T boost controller. It will be used to fine-tune the boost after Keith gets close by adjusting the wastegate springs. Anyhow, that's about all we can do on the engine stand. We'll have to take our Big 6 to the dyno cell to install the intercoolers and all the necessary plumbing. So this is what it looks like with everything completed, and a little extra plumbing to make everything work on the dyno. The intercooler setup may look spaced way too far out there. At least that's what I thought at first, but it's actually designed to fit on either side of the radiator in the Suburban. From this angle, you can also just see the blow-off valve right below the plenum intake. So after checking over everything one last time, we were ready to fire her up, run through the break-in process, and start making pulls. One of the first things we found was the engine was making way too much boost. Keith was having to pull back on the throttle at less than 4,000 RPM when the boost gauge was inching close to 10 pounds, which is our limit. That could be fixed by changing out the springs on the wastegates and a little fine-tuning on the boost controller. Keith Dorton and automotive specialists have become the go-to engine shop when it comes to creating one-off engines that have never been seen before. Many, in fact, were secret at the time, and he wasn't even allowed to talk about them. So at one point, while we were waiting for the engine to cool down a bit before making some adjustments, I asked him what draws him to unique engine projects like this.
I think the challenge is, always when we were doing NASCAR engines for decades, it wasn't as much of a challenge as what we'd like on a project like this. But the biggest thing then was the competition. Most of us that were engine builders in that era were friends. But, we done everything it'd take to beat the other one once we got to the racetrack. And I think that was good. That's gone, now in that type of racing because of, we won't go into that, but no, it's different. Now, the challenge of doing something that nobody else has done you know, I think that keeps me wanting to come to work, you know, every morning.
So finally, the fuel maps are dialed in, the boost levels are correct, and we are ready to make a power plant. You'll have to excuse me here. I had a brain fart and left the mic too hot, so the sound cuts out a little bit there, but you can still tell how great this setup sounds. Not the usual straight six clatter at all. Remember, this is not an all-out power build. With so many custom and hard-to-replace parts, not to mention the expense, Johnson's, an automotive specialist, had already set maximums of 10 pounds of boost and 500 horsepower. But by the time Keith pulled back on the handle at 5,200 RPM, we'd already exceeded 525. We saw peaks of 588 foot-pounds of torque at 3,700 RPM and 526 horsepower at 5,200. That 500 horsepower goal we hit early on at just 4,600 RPM. So, how much could this twin-turbo 6 make? You can see that the horsepower line has started leveling off by the end of the pull. But with more boost and more RPM, Keith believes 750 on pump gas would be pretty easy. But 500 horsepower when the tach is only at 4,600 RPM and more than 500 foot-pounds of torque all the way through the range will be more than the classic Suburban will be able to handle anyway. So, everyone's happy. And after more than 2 years of development, Keith was happy to send this 6 back to Johnson so they can complete the build. And he can start on his next one-of-a-kind project. Hey, thanks for watching, and please check out our other great engine build videos. See you next time.